Hello, this is question 7 from the 2021 MAT. Throughout this question, all functions will be Boolean functions of Boolean input variables. Boolean variable can be either 0 or 1. A Boolean function may have one or more Boolean input variables. And the output of a Boolean function is also either 0 or 1. Three elementary Boolean functions are defined as follows. Right, the function min of any number of inputs, so I've put k inputs into that one, outputs the value 1 exactly when each of its inputs is 1. Right, that is the output. The output of the function is the minimum value. Right, okay, that fits with the name. Then we've got max. Okay, I think we can see what that's going to be. It outputs the value 1 exactly when at least one of its inputs is 1. Okay, right, so we're putting in a whole list, a whole sequence, a string of zeros and ones, and min gives us the smallest number and max gives us the largest number. The function flip takes a single input and is defined as flip of x1 equals 1 minus x1. Right, so it's changing a 1 to a 0 and a 0 to a 1, so it's flipping them. First, we will consider Boolean functions obtained by combining the three elementary functions. One such function is shown below. So we've got some function f with 3 inputs, which is the minimum of the maximum of the 3 inputs and the flip of the minimum of the 3 inputs. Okay, describe in words when the function f outputs 1 and when it outputs 0. Right, well, if we describe 1, we've got the other because it can only output 1 or 0. So if we get when it outputs 1, then everything else is when it outputs 0 and vice versa. So which one? Let's say, okay, well, output 1. How are we going to get a 1 out of this? So we need to have max and flip both to be 1. In these, so one of these has got to be, at least one of them has got to be 1 in order to get 1 in the max bit. So therefore need at least 1 of x1, x2, x3 to be 1 to get max equal to 1. And we also need this flip of min to be equal to 1. So we need min to be 0 to flip it to 1. So we need at least one of these same ones to be 0 to get the other one, this flip min, to be equal to 1. Right, so that means we have to have a mix of zeros and ones. So describing words when it outputs a 1. So therefore output 1 when the input is a mix of zeros and ones. And then we can say it will output a 0 when all zeros or all ones. All zeros or all ones, as in the opposite case. Okay, that's the first part. All right, part 2. The function majority with k inputs outputs 1 exactly when strictly greater than half of its inputs are 1. Explain how you could combine elementary Boolean functions to obtain the following functions: majority x1, x2, and then majority x1, x2, x3. Okay, so we need to, for this majority x1, x2, so we have to have more than half of them equal to 1. So we need both of them. If they're both 1, we get a 1 out. And if they're not both 1, then we get a 0. Well, that's exactly the same as min. Do we need, it says explain. Well, I mean, that's, okay, maybe we could put a little bit on that then. So for, let's do i.e. if x1 equals x2 equals 1, then function returns 1. else function returns 0. Right, now if we've got 3 inputs, how are we going to work with this one? So for 3 inputs for majority, we need at least 2 of them to be 1s to return a 1. So how are we going to make sure that we've got at least 2 of them being a 1? We could look at, I suppose we can look at them in pairs. So if we look at them in pairs, then one of the pairs, providing we've got at least one of the pairs of numbers both being 1, then we're going to be okay, aren't we? So how are we going to put this together then? So we need, let's try and think about this. We're going to need to do mins of these. So if we do a min x1, x2, that will tell us if they're both 1, it will return a 1. If they're not both 1, it will return a 0. We need to find one of these. So I just wrote the m. Right, min x1, x3, because we need to find one of these pairs. Fortunately, there's only 3 pairs, so, and then x2, x3. So if one of those returns a 1, then we've got our majority. So we need to do a max around these. So yeah, max, right, so i.e. if at least one pair is 1, 1, then what we can say, then majority returns a 1. Right, so that seems fine with that. Okay, there's plenty more of this. I like to split this across a few sheets. Or is it 2 sheets? How many sheets do we have? Right, here's another one. Yeah, it's all on here. Still quite a lot to do. Now we will consider Boolean functions that can be obtained by combining only majority functions. Okay, there are exactly 16 distinct Boolean functions of 2 input variables. Okay, right, they've just dropped that one in. Well, I'll come back to that in a moment. Some of these can be represented using only majority functions that take 3 inputs. The use of 0 or 1 as fixed inputs to majority is permitted. For example, majority x1, x2, 1 represents the max function x1, x2. Yeah, it would do, yeah, because yeah, if one of x1 or x2 is a 1, then max returns 1, and then if one of them is a 1 here, then that little fixed 1 we're adding at the end, the third input, will turn that into a majority. That's fine. Find any 4 other Boolean functions of 2 variables that can be represented by combining 1 or more majority functions of 3 inputs. Right, so we need to find 4 of these, well, 4 more of these out of these 16. Right. Right, this is interesting. So yeah, coming back to this idea then, 16 distinct Boolean functions of 2 input variables. This might be new to some of you, depending on how much, well, Boolean logic or computer science or electronics or whatever else you might have done. If you haven't done any of that, this might be, you know, something of a bolt from the blue on this. So what they're really getting at on this is we've got some function. We got 2 input variables, right? So we got our function, whatever that is. It's going to do something. With 2 input variables, we can pass in 0, 0, 0, 1, 1, 0, or 1, 1. So we've got 4 different inputs that can come into our function. And out of this, we're going to return a 0 or a 1 for each one of these options. So we've got 4 inputs that are going to give 4 outputs, and each output has got 2 possibilities. So what we're saying then, so you could have one function where all 4 of them return 0. So they're our 4 outputs that we get from function number 1, say. You could have at the other end, let's call it function number 16. They've told us there's already 16 of them. They all return 1s. So that's another option. Now, the reason there's 16 of them is we can just count these up in binary. You know, we're doing 2 to the 4 essentially. You know, how how many options are there if we've got these 4 bits in our counting. So we got 2, 4, 8, 16 options. Yeah, we could have 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0. You know, we're just counting up here in binary, going all the way from 1 to 16. So they're our different distinct Boolean functions. And the ones that they've given us already, well, the min and the max ones anyway, not the flip one. The flip one will only have one input. It's not one of these options. But if you think of these 4 options that we've got coming in, 0, 0, 0, 1, 1, 0, and 1, 1. So if we were doing min would then have to return 0, 0, 0, 1. That would be the function out of these 16 that corresponds to min. If we were going to do max, it would be 0, 1, 1, 1. So we've already got our min and our max functions in there as it is. Now they've used the max one here. Now it's not a surprise that I'm going to jump straight to the min one, because we can see pretty quickly what that's going to be. You know, if they've given us this majority x1, x2, 1 for the max function, then min x1, x2 is pretty easy to see that it's going to be majority x1, x2, 0. So it's tipping the scales in favour of the zeros that are coming out of the majority function. So if we've got one of those x1, x2 being a 0, then it's going to be returning a 0, which is what we want from the min function. Now we need 3 more, I think it said, wouldn't it? Yeah, we have to find 4 others. So we've got those. So we can pick any 2 of these 16 have gone. We can pick 3 of the other 14. So what are we going to go for on this then? So we've got well, let's go for the extremes. These ones seem like good ones to go for. The one that always returns a 0 and the one that always returns a 1. So, I mean, these have got specific names. I mean, you don't necessarily need to know the specific names. You know, the one that always returns a 0 is called a null function. So the null function, that will be equal to majority, and we can put in fixed inputs. So great. I mean, we could put 0, 0, 0, or we could put, provided we got 2 of them being 0 at least, then that's going to be returning the same thing. We can do the same for returning 1s, which is called the identity. Now, if you don't know these terms, null and identity, just say the function that always returns a 0, the function that always returns a 1. You don't need to know the technical terms for these in order to get the mark. So this one, we could say majority 1, 1, 1. That gives us the identity. Right, so now we need another one, which is going to return, well, what do we want it to return? There's quite a few things. I'm just trying to think of, well, what would we have for, well, let's have the one that always matches x1. So if we had the one that went 0, 0, 1, 1, so the output of this is always x1. It's always our first column. Whatever we put in as the first input, that is what we're getting coming out. So this is called the transfer function. So we could have a transfer for x1. So i.e. we're just getting x1 out of our function, and we want a majority for that then. So that would be equal to majority. And we could just put, well, x1, x1, and again, we could have anything for the third argument. Let's just put 3 inputs of x1, and then it's going to return x1. So, yeah, I mean, I think that could be a little tricky, that question, if you haven't come across this idea before or used any of these Boolean functions. I think you could find this one a little bit tough, that part 3 there. You know, it's taken up quite a lot of time in the video as well, explaining it all, but I think it's useful. It's worth going away and having a look at this, because then you'll get an idea of what all of the different names are as well. Like they don't call these, you know, for min, this would be an AND function. And for the max would then be OR, I think, if I've got that the right way round. I think that would be right, trying to think it through in my head. But then you get all of the other sort of exotic, your NANDs and your NORs and all this sort of stuff in there. So they've all got these different names. The flip functions will be equivalents of NOT functions. So you'll have NOT functions, and then towards the end of them, you get what are they, implications, and I'm trying to remember the name of the other one. It's been a while since I've done these. Inhibitions, I think it is, something like that. But anyway, it's quite interesting to look through them, so I recommend going off and having a poke around on some of those. Anyway, that's part 3. So let's hopefully get I've only got 2 more bits on here. So part 4, let's see if I get it on this sheet and then get a new one up. Give an example of a Boolean function g of 2 input variables that cannot be represented by combining majority functions of any number of inputs. Right, you should write your answer by explicitly specifying the 4 different inputs. So, right, we want something that can't be covered by a majority. So majorities are very much turning what we're putting in is picking out one of the input variables. You know, we can see it like with this one here when we're doing a transfer. Okay, it's specifically looking at x1s and then returning something to do with x1. I'm not sure how majority, I'm leaning towards something to do with flip, because I'm not sure of a majority one, how we're going to be able to get the opposite of something. I think anything which is doing a not or a variation on a not, I think we're going to get stuck with. So say, let's run with this for a bit and see where we end up. So say we had our g of x1, x2 was going to be equal to flip of x1. So that is what our function is. We passed in these 2 inputs into g, but g is only dealing with x1 and is going to return whatever the flip is. So we need that g, so 0, 0, g, 0, 1, g, 1, 0, and g, 1, 1, oops, 1, 1, is going to flip. So we get 1, 1, 0, 0. It's flipping our first input. So are we going to be able to get a majority function with any number of inputs? Okay, any number of inputs. I've changed it a little bit here, but any number of inputs that is going to give us that. I mean, if we were going to have a majority, I'll just put MAJ, you'd have to have an x1 in it, that's for sure. But we can't, if we're only doing majorities, and we can't just do majority x1 because it's going to return us x1 and we want to flip it. And we've got no way of knowing what other, x2's got nothing to do with x1. They're just not related, they're independent. So passing x2 in isn't going to help. And passing in fixed 0s and 1s isn't going to help either, because we don't know what x1 is. And we need to get the opposite of it. So yeah, we're never going to be able to deal with that. You know, x1 needs to be in it, but it's got to act against it. You know, that's not the nature of the majority function. So how much did it want? It says justify your answer. How on earth am I going to justify that? Right, it's not easy to explain. Right, so x1 would need to be an input to majority, but we would need to know flip x1 in advance for majority to work, for majority to replicate G. Okay, I've kind of scattered that around, but hopefully you can see what I'm getting at. As is often the case with these questions, actually giving the justification is the hardest part. You know, it's so often the case. But yeah, we're just not going to be able to do anything that involves some kind of flipping, some kind of not. So, right, that was another fairly tricky bit, I think. Right, let's get a fresh sheet up for the last part, because that's really cluttered up. Part 5, consider 4 input variables. Okay, x1 to 4. Let z1 be the minimum of those two, z2, z3, z4. Right, so we've paired them off in, or some of the pairs anyway, and taken minimums. It is sometimes possible to represent a function s with those 4 inputs using a function t with the z inputs. For example, min x1, x2, x3, x4 is min of the z's as both functions output 1 if and only if all 4 x's are 1. Okay. Can you represent the following functions of inputs as some Boolean function of inputs? Right, okay, so can we switch the x's to z's in majority and still get the same thing? So what do we want then? So in majority, that means we need to have 3 or 4 of xi being equal to, well, the same thing if we want to get a 1 out. So are we going to be able to do that? Equals 3 or 4 of them need to be equal to 1, then we get a 1. Or if it's 0, then we get a 0. Right, so how are we doing this then? How would we be able to deal with this? We need, I mean, if they're all the same, then, well, what are we doing with these z's? If we've got 3 or 4 of them, I mean, we've got at most one of them is going to be a 0. So out of these z's, we've got at least 2 of the z's would have to return 1s because each one appears in 2 mins. So at most we can get 2 zeros out of the mins. So that would be fine, wouldn't it? So, right, so if majority returns a 1, then at most 1 0 in inputs. Right, therefore at most 2 zeros in the Z options, ZI. Okay, so we can stick the ZI's into a majority and then we'll be all right. Providing we've got an extra input, because we could be split 2-2 otherwise. So therefore we can say that majority x1, x2, x3, x4 will be equal to majority z1, z2, z3, z4, and then we need to put in another number, don't we? Actually, how's this going to go? Yeah, because it's just going to be the opposite. I was just wondering what we put in. If we put a 1 in at the end, then we'll be fine, because if we've got, I'll just have to double check this with the zeros. Right, so that definitely works. If you've got, it's going to return, well, if it's turning a 1 in the same case, it must be returning zeros in the same case. We can't have a gap between the two of them. So if they're all 1s, then all the x's are 1s, then all the z's will be 1, and we get a majority. If we got 1 0 in amongst the x's, then we'll have 2 zeros amongst the z's. So we'll have 3 to 2 on the 1s to 0, so that will work. And then for anything else, then we're going to get zeros coming out, aren't we? Because if we've got, so if we had 2 zeros in the x's, then what are we getting? 2 zeros amongst the x's. That means we'd have 3 zeros amongst the z's. Right, so if xi contains how many zeros? So if we got, okay, so we'll have no zeros, 0 zeros, 1 0, 2 0, 3 0, 4 0. Then we can say that zi will get 0 zeros. Then if it's got 1 0, it'll have 2 zeros. If it's got 2 zeros, it would have 3 zeros. And then it would have, for 3 zeros, it would have 4 zeros, and then that would be 4 zeros. Right, so we've got those, which means we'll get an output on each one of these of, so what we get in the output then, let's put these in red. The output there would be 1, would be 1, would be 0, would be 0, would be 0. Here the output would be 1, would be 1, would be 0, would be 0, would be 0. Right, so that does fit. Okay, again, that's taken quite a long time to figure that one out. Right, so the other one is parity. Outputs 1 exactly when an odd number of its inputs are 1. And right, okay, so we need an odd number of inputs. So we get that this is equal to 1 if 1 or 3 inputs equal 1. Right, okay. So if we add, oh my word. Right, so say we had one of them. If one of them was in because that just seems easier to deal with. So if one input equals 1, then Zi, they're all going to be equal to 0. So, well, that's going to cause a problem, isn't it, straight away? Because that's going to be indistinguishable to having all of them being equal to 0, isn't it? Yeah, okay, so let's say that then. So parity, right, parity. So say we add 1, 0, 0, 0, that is equal to 1. And parity 0, 0, 0, 0 would be equal to, or not 0, not 1, 0. So those things need to be different. But if we've got these two x values, these two sets, both sets give Zi equal to 0. Because if we pair off all of them and do mins of them, every single pair is going to give 0 for both of them. So therefore we've got lost information and we cannot distinguish between these two cases using Zi. Cannot distinguish using Zs. So that isn't going to work. Right, that was a bit quicker, the last one, than doing the majority one. Right, that was a very long question. I think that was a difficult one. It was, I think that's the most difficult one on this paper and one of the more difficult question 7s that there have been. So it started all right, part 1 and part 2, but then part 3 was, I think, particularly difficult. Particularly, especially if you haven't come across that sort of terminology before and thought about these Boolean functions, then part 3 was difficult, 4 was difficult, 5 was difficult. So I would say that was a pretty tough question, as reflected in the length of this video, which must be one of the longest ones that I've done on a math question, I would have thought. But there you go, that's wrapped up paper 2021. Always nice to get another one done.